Kia ora tātou, my name's John Moore and I'm the Research and Development Manager for Timberlands. It's my pleasure to welcome you to the annual Forest Growers Research Conference, which unfortunately, like last year, due to COVID, is an online conference. My presentation today focuses on the work that we're doing at Timberlands to better understand the wood quality in our estate through the application of new technologies.
As forest growers, we focus on growing the maximum volume of the most valuable log grades. These grades are mostly determined by external attributes such as diameter, length, taper, sweep, and branch size. However, internal attributes are also important for many of our customers, as these determine the performance of the end products they make. These performance requirements depend on the product being considered, but can include attributes such as strength, stiffness, dimensional stability, colour, appearance, durability, tear, burst, and tensile strength. Forest growers generally use surrogates for these requirements, as these are attributes that can be measured in the field. These surrogates include density, microfibril angle, acoustic velocity, heartwood content, branch size, resin pocket incidence, and compression wood content. As managers, we would like to understand the impacts that our forest management practices have on internal wood properties and the potential implications for the performance of the current suite of products made from our resource, as well as for new products that may be made from it in the future. At Timberlands, we are focused heavily on increasing forest productivity through tree breeding, including the deployment of elite clones, enhanced forest nutrition, and changes to our silvicultural practices. There have been concerns around the impacts of productivity on enhancement on wood quality. Take genetics, for example. We know that traits such as density and stiffness have adverse genetic correlations with growth traits, and this was particularly apparent in clone 55. Nutrition is another area where there was the perception that applying fertiliser would lead to a reduction in wood density. Finally, if we do manage to increase productivity, it follows that rotation age will reduce, and here again there have been concerns expressed that wood quality will suffer. Therefore, it is important for us at Timberlands to understand the impacts of our productivity enhancement strategy on wood quality. Wood density has been one of the most widely studied wood properties due to its relative ease of measurement and the fact that it is correlated with many other wood properties and some aspects of end product performance. Outer wood density samples are particularly easy to collect, and large numbers of these have been collected through density surveys undertaken by FRI, as it was at the time, and as part of numerous research studies. Analysis of these data can be used to show the regional level variation in wood density that exists, which is useful for strategic decision making around fibre supply. At Timberlands, we have collected numerous outer wood density cores as part of our pre-harvest inventory program and more recently our age 10 inventory program. Here too, we can see that density varies significantly across our estate, mostly driven by differences in mean annual temperature. Studies such as the benchmarking study carried out by the Wood Quality Initiative in the early 2000s gave us some new insights into the internal variation in wood properties that exist within and among trees. The three examples in this slide show the average radial and longitudinal variation in wood density, microfibril angle, and modulus of elasticity that exist within a tree. Each figure represents a vertical slice through the stem, with the pith on the left-hand side and the bark on the right. What is apparent from these graphs is the core wood zone near the pith that contains wood with low density, high microfibril angle, and low stiffness. A question for us as managers is, are we stuck with core wood, or is there something that we can do about it? Often an arbitrary definition of the innermost 10 rings at all heights up the stem has been applied, which suggests that rotation age is the only option to manage core wood. However, we believe that it could be possible to manage core wood through other means, such as tree improvement and silviculture. For us at Timberlands, this is why we are so interested to know much more about wood properties beyond just outer wood density. The other reason is that we want to avoid any unpleasant surprises, such as this. As much as I'd like to say this disc did not come from our estate, this would simply not be true. There are a wide range of non-destructive evaluation techniques and tools out there that are able to provide estimates of different wood properties. Most of you are probably familiar with portable acoustic tools, such as the ST300 and HM200 developed by Fibergen, that have been widely used in New Zealand and overseas for resource characterization studies. You are probably less familiar with tools such as the resistor graph, CoreBot and DiscBot. The rest of my presentation will focus on how Timberlands are using these tools to better understand our resource and the impacts of some of our interventions aimed at increasing productivity. The studies that I will present are very much a work in progress, but the aim is to provide you with an overview of the types of questions we are asking, the tools and techniques we are using to answer these questions, and the results we have obtained to date. Before I launch into that, I'd like to acknowledge and thank colleagues at Scion who have done the collection of Resi data, collection and analysis of CoreBot cores, and the scanning and analysis of DiscBot samples. They have also been instrumental in developing and in further enhancing these systems to help answer our questions of interest. I'd also like to thank my colleagues at Timberlands and our contractors who have helped with the disc collection. Unfortunately, we haven't yet managed to automate disc collection, so we rely on the sterling efforts of people in the field to collect our samples. The first study I'd like to discuss focuses on examining the differences in core wood properties among selected clones. As many of you are aware, Timberlands has been deploying clones operationally since around 2008. Currently, about 25% of our new plantings are with clonal stock. Each year we plant establishment archive trials which contain all our operational seedlots and clones planted in 100-tree plots on the same site in a replicated design. We've been doing this since 2004, so have amassed quite a lot of data. Last year we carried out non-destructive and destructive sampling of a selection of production clones to assess wood and fibre properties. We even removed billets from selected clones for pulping studies to see if there were discernible differences in pulp and paper characteristics. Overall, 6 production clones were sampled in 2 separate establishment archive trials located in different parts of our estate. 12 ramets of each clone were sampled at each site, along with 12 trees from a reference seedlot 99185. Some of you will probably be familiar with this seedlot, which has a nominal GF19 rating and is used as a control in many large plot genetic gain trials. It is supposed to represent the level of genetic improvement in the crop that is currently being harvested. We also selected another seedlot 08502, which had high GF plus trait ratings for both growth and wood density. On each selected tree, information on DBH, total height and green crown length were collected, which revealed some differences among genetic entities. Bark-to-bark resistance traces were recorded at breast height with the resistor graph, along with bark-to-bark cores. Standing tree acoustic velocity measurements were made using the ST300 tool. Resistance traces were processed using the Resi processor software developed by Jeff Downs of Forest Quality in Australia to obtain predicted density and acoustic wave velocity. The bark-to-bark cores were scanned with the CoreBot, which is Scion's DiscBot modified to take core samples. For each core, information on density and chemical composition were obtained. From these measurements, we found that there were large differences in wood density among the clones. Clones A and B had much higher values of density than the other clones and the reference seedlot at both archives trials, as shown in the 2 panels in the left-hand half of the slide. We also found that the resistor graph tool was very good at predicting average core density at the individual tree level, as shown in the panel on the right. This demonstrates the utility of this tool for rapid wood quality assessment, at least for wood density. Moving on to wood stiffness, we again see large differences among the genetic entities in the trials, but these differences do not mirror the trends observed for wood density. For example, clone C, which had low wood density, had relatively high wood stiffness measured on both the standing tree and felled stems. This is not unexpected, as wood density and wood stiffness are not well correlated in the core wood. What it also highlights is that simply relying on wood density as an indicator of core wood quality could lead to some erroneous conclusions. We observed a positive relationship between tree slenderness, or height to DBH ratio, and acoustic velocity measured on standing trees. This showed that individuals that were more slender had higher stiffness values, which has been demonstrated previously in a range of trials. Regarding wood chemistry, we observed substantial differences in whole core average values of lignin and glucose content. This information, along with data on fibre properties and handsheet properties, is useful for the pulp and paper industry when evaluating genotypes in terms of their suitability for pulping. We're still working through these data to better understand what they are telling us. We also felled each tree that had standing tree measurements made on it. From each tree, 4 discs were collected up the stem at 1.4, 3, 6 and 9 metres. These discs were scanned using the DiscBot to yield information on the distributions of density, wood stiffness and chemical composition within a disc. These maps are helping us to understand patterns of variation in properties, such as the extent and severity of the low stiffness region and the amount of compression wood. As I noted earlier in my presentation, this is still a work in progress. To help with this type of analysis, Scion have been developing algorithms that automatically detect ring boundaries so that we can map wood properties to a specific year. This enables us to identify age-related trends and the impacts of treatments that occurred in a specific year, such as a thinning or a fertiliser application. Ring detection might sound like a trivial task, but I can assure you that it is not. Many very clever people have tried to do this with limited success, which is why it is very exciting to see the progress that Christine Todoroki at Scion has made. She appears to have cracked this problem, which will enable much more detailed analysis of our DiscBot data. Without going into a lot of detail, her approach identifies rings based on the density information and essentially unwinds the disc, flattening out the data before fitting smoothing splines to detect the ring boundaries. Another focus area for us at Timberlands is forest nutrition. We have been investigating mid-rotation fertiliser applications for many years, but in 2018 we worked with Scion to install large replicated trials testing different rates of a fertiliser blend that was developed to deliver the optimum ratio of nutrients required for tree growth. At all 3 sites where we applied this blend, we have seen large positive growth responses relative to the untreated controls. In some cases, the volume growth after 3 years has been up to 50% higher in the treated plots relative to the untreated controls. As I mentioned earlier, there have been concerns raised in the past about the potential impacts of fertiliser application on wood properties. However, recent work by Scion, which looked at samples collected from the long-term site productivity trials, showed that there were few, if any, adverse effects of fertiliser application on wood properties. In these trials, particularly the one at Woodhill Forest, fertiliser was applied at rates far in excess of what would be done operationally. Nevertheless, we still believe that it is important to test whether our nutrition strategy might have any adverse impacts on wood quality. It's better to find out now than learn the hard way in years to come. We are in the process of collecting data from the nutrition trials that were installed in 2018. However, we did collect samples from an earlier trial in 2020, which compared the growth response of plots receiving 450 kilograms per hectare of urea to untreated control plots. In this trial, we sampled 10 trees from each treatment. Tree size measurements were made and 4 discs were collected from each tree at 1.4, 3, 6 and 9 metres up the stem. Acoustic velocity was measured on the felled stem using the HM200 tool. There were minor differences in tree size observed between the trees sampled from the 2 treatments. There was also a slight reduction in HM200 acoustic velocity in the trees that received fertiliser. We also observed some examples of interesting patterns of wood properties from the DiscBot data. We found some discs where there had been a slowing of growth followed by a rapid increase. The disc shown in the slide actually came from a plot that had not received fertiliser, so it is more likely to be the result of the tree being released from local competition. What it does show is the rapid increase in growth was accompanied by the production of a large amount of compression wood, which has lower stiffness as seen in the middle plot and higher lignin content as shown in the plot on the right. Fortunately, this was not a common occurrence, but it does serve to illustrate what rapid changes in competition may do to wood properties. We are also doing more detailed investigations into the effect of spacing and thinning on wood quality, particularly in light of the result that we have just observed. The effects of spacing on tree growth and morphology have been extensively studied. Tighter tree spacing leads to more rapid crown recession, resulting in a tree with smaller branches and higher height to diameter ratio. It also reduces radial growth as shown in the figure on the left. In 2020, we installed 2 trials to investigate whether it was possible to control core wood extent and properties through manipulating initial planting spacing. These trials contained initial planting densities ranging from 625 stems per hectare up to 1,515 stems per hectare, which was pretty much the upper limit of what our spot mounting operators could achieve. Obviously, these trials are going to take a while to yield any useful data and results. However, we were fortunate to discover an old trial on our estate that was established by Fletcher Challenge Forests. This trial included 4 levels of initial planting density, 350, 550, 750 and 1,000 stems per hectare. The intention was to thin all plots to 350 stems per hectare, not that long after planting, but this never happened, so this became a plant and leave trial. This enabled us to look at the impact on core wood properties. We sampled 10 trees from each of the 4 initial planting densities. As in previous studies, we collected 4 discs from each tree at different heights up the stem. At the whole disc level, we can see large differences in wood stiffness, or ultrasonic velocity, among the spacing treatments. Trees planted at the widest spacing, 350 stems per hectare, had lower stiffness, particularly at breast height. This is shown as treatment C on the graph. Differences in wood density among treatments did exist, but these were not as pronounced as differences in stiffness. Looking at a selection of discs from this trial, the larger core wood zone in the trees planted at 350 stems per hectare is apparent in the middle column of the left-hand panel, which shows the lower ultrasonic velocity, and in the right-hand column showing the higher lignin content. Again, once we can apply the ring detection algorithms to these data, it will be possible to undertake more thorough analyses to quantify these differences in core wood properties. Finally, we are also investigating whether it is possible to reduce harvest age under certain conditions and still provide our structural sawmill customers with an acceptable product. Reducing harvest age with no loss in quality would enable us to capitalise on our productivity enhancement work and is also a mitigation against future climate change risk, as my colleague Ian Hinton will discuss in a later presentation. Each year we identify a number of stands in our harvest level and valuation estate model that could be harvested early were it not for a minimum harvest age criteria that we impose as a constraint. One of these stands is in Tarawera Forest, and we looked at it for a potential young age harvest when it was 15 years old. Without more detailed analyses, we were not comfortable simply sending logs to the mill and seeing what resulted. Last year, when the stand was 17 years old, we felled 15 trees and had 60 discs analysed with the DiscBot. We also took log sonic measurements and outer wood density cores. The log sonic measurements were mostly above 2.85 kilometres per second, and the breast height outer wood density was almost 450 kilograms per cubic metre. Analysis of the discs has indicated that the core wood zone appears to be restricted to the innermost 6 rings, and if a sawmill was to box this out during processing, an acceptable yield of structural timber could be obtained. To sum up, tools such as the CoreBot, DiscBot and resistograph enable us to gain more insight into wood property variation and its drivers than simple point measurements. We've begun to apply these tools to obtain more information on how factors such as genetics, nutrition, management, tree spacing and rotation age affect wood properties and the potential impacts for our customers. There is still much to do in this area, as ensuring that our productivity enhancement strategies don't have an adverse impact on wood quality is key to their success. What we've observed so far shows us that it is important to understand the growth dynamics of trees in order to better understand wood property variation. We are fortunate to have built up a good data set in a relatively short period of time, and more detailed analysis of these data using new analytical methods will yield further insights and much valuable information. Working with organisations such as Scion and FWPA is allowing us to access these improved analytical methods. Finally, we are continuing to collect new data from a range of experiments throughout our estate, which will help us provide further clarity on the properties of the future resource that will come from our estate. Thank you for listening, and I look forward to meeting with you in the panel discussion later.